Hello everyone, I once again welcome you back to my YouTube channel. This is going to be my third video on the topic of electrostatics. In this video, I'm going to talk about problems in electrostatics for second PUC or for your class 12 board exam. So I've divided the type of problems on electric charges and field basically into two types. The first type is just an illustration of Coulomb's law. The second type is going to be based upon superposition principle and Coulomb's law. On Coulomb's law, we'll see two illustrations, basically pith ball concept and charge sharing concept. So these are two types of illustrations that I would like to talk to you about from the point of view of Coulomb's law. Under superposition principle, we will be talking about null point problems and net electric field in case of regular geometric shapes such as squares, rectangles, and triangles. So without any further delay, let me start off with question number 1.12 from your NCERT textbook. As you can see, I already have your textbook in a split view screen. Take a look at the question 1.12a. The question reads, two insulated charged copper spheres A and B have the centers separated by a distance of 50 centimeter. What is the mutual force of electrostatic repulsion if the charge on each is 6.5 into 10 power minus 7 Coulomb? The radii of A and B are negligible compared to the distance of separation. Let me explain to you the question. So we have been given two copper spheres A and B. Each copper sphere is having a charge of 6.5 into 10 power minus 7 Coulomb. The charges on them is both the same and the distance of separation is 50 centimeter. So this is what we have been given and we are asked to find force. So the electrostatic force of attraction or repulsion between any two spheres. In this case, you will have to note that the radii of A and B are negligible compared to the distance of separation, which means we can treat both the spheres as point charges. Because we can treat them as point charges, we can directly apply Coulomb's law. From Coulomb's law, the expression reads, the force of attraction or repulsion is given by 1 by 4 pi epsilon naught QA QB by R square. So plugging in all the values given to us, we see that the force of attraction or a force of repulsion rather between both the spheres is about 1.5 into 10 power minus 2 Newton. A straightforward problem. All that you had to do was to just substitute the given values into the particular formula and get the answer. Take a look at question number B. Question number B reads, what is the force of repulsion if each sphere is charged double the amount and the distance between them is halved? So the question reads, you're doubling the charge on both the spheres and distance between both the spheres has become half. So initially, what is the force between both the spheres? We know that initially it is 1 by 4 pi epsilon naught Q square by R square. Because QA is equal to QB and this is equal to Q. Let's call that as Q itself. So this is the initial force. So finally, when the charge is doubled, that means on each sphere, if the charge on one sphere is Q, it becomes 2Q. On other sphere also it becomes 2Q. So which is already shown here. And the distance R has been modified into R by 2, right? Because the distance has been halved and charge on sphere has become doubled. So once we take a look at this, once we include all the parameters in this equation, finally, and you make certain simplification, we see that the force becomes 16 times that of force initially when you double the charge on each sphere and when you half the distance between both the spheres. So the final force is going to be 16 times more stronger than the initial force. So these type of problems are extremely important in your competitive exams. So such questions may be asked, right? So it is very important to keep a note of such problems. Moving on to next question, 1.13. Suppose the spheres A and B in exercise 1.12 have identical sizes. A third sphere of the same size but uncharged is brought in contact with the first, then brought in contact with second, finally removed from both. What is the new force of repulsion between A and B? Right, that's quite a mouthful amount of question, but let me break it down for you. So initially, take a look here. We are given, let me change the color here. Initially, we have both spheres A and B, let's call them, and they are identical. So the charge on each sphere is about 6.5 into 10 power minus 7 Coulomb, which is equal. And there is another sphere, which is an identical sphere. It doesn't contain any charge. The charge on C is 0. When this sphere is brought in contact with A, what happens? When you bring an identical sphere, a charged or uncharged sphere, and you put it in contact with another sphere, charge is going to be shared. How is it going to be shared? It is going to be shared equally. Why is it going to be shared equally? Because they are identical in nature. So after contact, so once you make a contact of A with C or C with A, what is going to happen is the charges are going to share identically, right? Or equally rather. So what happens is, so the charge on A is about 6.5 into 10 power minus 7 Coulomb. Let me minimize the screen. 6.25 into 10 power minus 7 Coulomb. While the charge on another sphere is going to be 0, because that is what has been given to us. Once you plug in all the values, we see that we get 3.25 and into 10 power minus 7 Coulomb on sphere A as well as on sphere C. So finally, we have a situation once you make the contact with C. So A is going to have a charge of 3.25 into 10 power minus 7 Coulomb, and C is also going to have a charge of 3.25 into 10 power minus 7 Coulomb. Now the next question reads, C is brought in contact with B. That means C is already having a charge of 3.25 into 10 power minus 7 Coulomb. Now this is brought in contact with B. What happens again? Charges are again shared. How are they shared? They are shared equally, right? So further, what do we have? It would be 6.5 into 10 power minus 7 Coulomb, which is a charge on B. And 3.25 into 10 power minus 7 Coulomb is charge on C. So divided by 2, we get the final charge on B and C is going to be 4.875 into 10 power minus 7 Coulomb. Meaning, B, which was having initial charge of 6.5 into 10 power minus 7 Coulomb, will end up with a charge of 4.875 into 10 power minus 7 Coulomb. Right? C also has about the charge, same charge, which is going to be 4.875 into 10 power minus 7 Coulomb. Now from the question, it says that C has been removed and A and B are replaced at same distance. So the final charge on A, as already calculated, is about 3.25 into 10 power minus 7 Coulomb. The final charge on B is going to be 4.875 into 10 power minus 7 Coulomb. So distance is going to be 50 centimeter because they've been replaced at the initial positions once again. So we once again use Coulomb's law to find the force. Plugging in all the values, we see that the final force is going to be 5.7 into 10 power minus 3 Newton. Charge sharing concept has been asked various times in CET exam as well as in NEET exam. It is very important for you to remember the concept of charge sharing whenever you have spheres that are brought in contact. If they are identical, then charge sharing happens equally. Charge is distributed equally among them. Right. Moving on to next illustration. The second illustration that we would be talking about is the problem of pith balls. So let's take a look at what this pith ball problem is all about. So we are given a question. 2 pith balls, each of mass 5 into 10 power minus 4 kg, are suspended by silk threads, each of length 0.2 meter from same point, and are given same charge. They separate till the angle between the threads is 60 degrees. Calculate the charge on each pith ball. Pith balls are basically, you can call them as like some kind of pendulums, A and B. Let me change the ink here. Yeah. This is what the situation has been depicted in this figure. We have 2 balls which are suspended from the same point by means of a silk thread. And they're supposed to have same charge. They are given same charge. Because they are given same charge, what happens is they'll start repelling in opposite directions, and they settle down at an angle of 60 degrees. This 60-degree angle is said to be what angle? This is an equilibrium angle. This is an equilibrium angle. Length of thread is being given to us, but the distance between pith balls is not given, which can be calculated using simple trigonometry, which I will show it to you. So we are asked to find the charge on each pith ball. So basically what we'll be doing is we'll be using Coulomb's law. Coulomb's law to solve the problem, and also simple Newtonian mechanics. Newtonian mechanics to solve the problem. Right. Moving on. So this is what has been given to us. Both the masses are same, and the masses are 5 into 10 power minus 4 kg. Length is 0.2 meter. This is the length of the string. Length of the string is 0.2 meter. Equilibrium angle is 60 degrees. Distance r is not given to us, and charge also has to be determined. Now first let us work out what is the distance between the pith balls. From simple trigonometry, it is easy to notice. If this is pith ball A and this is the perpendicular, so this is going to be 30 degrees. And this length has been given to us 0.2 meter. From the diagram, this is going to be r by 2, right? From this point to this point, the distance is going to be r by 2. From this point to this point, it's going to be r by 2. So the final distance is r. So therefore, to find this particular length of the side, we'll be using sine, because this is the opposite side. So we have sine 30. It is going to be, this is opposite side and this is hypotenuse. It is easy to identify that. Is going to be opposite by hypotenuse, which is nothing but r by 2 into 0.2. Correct? Sine 30 is basically 1 by 2 into 2 into 0.2, which is equal to r. So therefore, r is going to be, did I make a mistake somewhere? I think so. No, let's keep it that way, right? R will be equal to r by 2. This is going to be r by 2. Yeah, r by 2 into sine 30 into 0.2. So r is going to be 2 times sine 30 into 0.2. Correct. There's no mistake here. Right. So since equilibrium angle has been given to us, what does equilibrium actually tell us? Equilibrium actually refers to net force has to be 0 everywhere. Right? So for the net force has to be 0, forces have to be balanced. That means the component of sigma fx, correct? The acceleration along x-axis should be equal to 0, and similarly acceleration along y also should be equal to 0. This is what it implies. The components of forces acting on the pith ball should add up to 0 along all the axes. Because this is a two-dimensional problem, we'll only be dealing with x-axis and y-axis. Now let us consider pith ball A. One can also consider pith ball B. Now let us make the list of forces acting on pith ball A. What are the list of forces acting here? It is easy to notice that on pith ball A, there are forces such as gravity, which acts vertically downwards. And then there is electrostatic repulsion, which acts in the x-axis direction. And then there is tension due to silk thread. Now let us make a free body diagram of A. I've made a free body diagram already here by choosing XY axis as my coordinate system. As you can see, tension is in the first quadrant, and this angle turns out to be 30 degrees. Why is it 30 degrees? Because this angle here is 30 degrees. If you drop a perpendicular here, this is also going to be 30 degrees because those are alternate angles. Now there is tension acting in first quadrant, and electrostatic repulsion for pith ball A is along negative x-axis. This is along minus x-axis. and weight which is acting along negative y-axis. So for equilibrium, we are going to balance the forces. Balancing the forces along the x-axis. What are the forces along x-axis? There is the component of tension, which is this particular length. This particular length is going to be t sine 30, because this is going to be parallel to that side. Therefore, it is going to be t sine 30. T sine 30 is balanced by electrostatic repulsion, that is Fe, which is given by 1 by 4 pi epsilon naught q square by r square. I have plugged in the values, and r, as already remarked, is going to be 2 into sine 30 into 0.2, which I have already shown it here. So this is going to be r square. Similarly, one can do the same exercise along y-axis. Balancing along y-axis, we see that along y-axis there is a component of tension, which is this particular length. It's going to be that's going to be t cos 30. That's going to be t cos 30 along y-axis, positive y-axis. Along negative y-axis, we have mg, which is the gravitational force acting vertically downwards. Now, mass of the pith ball is given to be 5 into 10 power minus 4, and g value is 10 meter per second square, that we are going to make an assumption instead of 9.8, just for sake of convenience. So this is going to be 5 into 10 power minus 3. So from equation 2 and 3, we have two unknowns basically. One is tension is not known to us, and also the charge on each pith ball, which is supposed to be calculated. What we do from equation 2 and 3 is we are going to divide both the equations 2 and 3 so that we can eliminate the tension. So dividing 2 and 3 and solving for q, we find that q is going to be 0.112 into 10 power minus 6 Coulomb. I've shown the simplification here. Kindly go through the simplification part. Now, knowing charge, this was the only parameter that has been asked to us from the question. One can always substitute the value of q in equation 2 or in equation 3 to find out tension, which I will leave it as an exercise for you. So we have basically solved two types of problems as an illustration of Coulomb's law. That is, first one is the concept on charge sharing, and second one is based upon the pith balls. Pith balls where we've used both Coulomb's law and Newton's laws to arrive at the solution. My suggestion to you would be to go through your NCERT textbook and solve problem number 1.1. Let me just write down here. You can solve problem number 1.1, problem number 1.2, and you can also solve problem number 1.5 as an assignment work. Yeah, those are the three types of problems that I want you to solve based on Coulomb's law, direct application of Coulomb's law. Moving on, let's consider type 2 case of problems. Type 2 case of problems are based upon null point problems. These are very important kind of category. They have been asked multiple times in your board exams. What does this null point actually mean? Null point actually means E net at that particular point will have to be 0. Because net electric field is 0, F net is also going to be 0. Why is F net equal to 0? Because F net is QE net. Therefore, F net also turns out to be 0. Such questions have been asked, like I've already remarked, multiple times in your board exams as well as in competitive exams. So let us take a look at the first question. In this question, we are given two charges. Okay, I think we'll have to make a few changes here because, okay, let's change the values from 2 and 4 to 4 and 16 because I think it is going to be much more simpler. Much more simpler to solve. Just a moment. Let me solve the question for you. Let me erase this completely so that you can get to see the directions of electric fields clearly. I should not have written this. Anyway, no problem. Let me just solve it for you clearly so that I don't have to write once again on the screen. It becomes a mess. Let me write it once for you so that you can identify the directions of electric field. This is a very important type of problem. So let me rewrite it for you. Two and 4 make algebra a little difficult. 4 and 16 are much more convenient as an illustration part. Okay. So we are given two charges. The two charges are 4 into 10 power minus 6 Coulomb located at A, and there is one more charge 16 into 10 power minus 6 Coulomb located at B, and the distance of separation between both the charges is given to be 6 meter. So as already remarked, null point refers to a point where net electric field is 0. The first point to keep in your mind is that it is usually found near the smaller charge. In this case, which is the smaller charge? The smaller charge is 4 into 10 power minus 6 Coulomb. Right. Now this null point, like I've already said, so let us take two positions A and B. This is 4 into 10 power minus 6 Coulomb, and this is about 16 into 10 power minus 6 Coulomb. So it is near the smaller charge. It can be either to the right hand side of 4 into 10 power minus 6 Coulomb, or it can be to the left hand side of 4 into 10 power minus 6 Coulomb. Now to determine the exact point or the exact location of null point, what we shall do is we shall use vector addition of electric fields. Wherever the net electric field balances or cancels, we can find a null point. If at all the electric fields add up, then we know that for sure that E net can never be equal to 0. Now let us consider one such particular position. I will choose it to the left hand side first. Left hand side here. Let's say this distance is at x from A, right? This point C, I will call that as null point, and I will assume the distance from A is about x meters, and from x to B, this distance is 6 meters, which is already given to us, and this distance is going to be 6 plus x. Without actually solving, let us just find out whether C can be a null point or not. At C, we know that at A and B we have two positive charges. The direction of electric field due to positive charge, already remarked in the previous lecture, is going to be radially outwards. Right? So the direction of electric field at point C will be contribution due to electric field due to A, which I will call it as EA, and electric field due to B, which I will call it as EB. Now the directions at C, because A is a positive charge, it is going to be away from A, meaning the direction of electric field is going to be away from A. Therefore, this is the direction of EA, right? It is going to be away from A. Similarly, what is the direction of electric field due to B at point C? Because B is also positive charge, electric field will be pointing to the left hand side itself, away from charge B. So the net electric field, because the directions of electric fields are in same direction here, we see that EA plus EB, can this ever be 0? This can never be equal to 0. So this is the concept of vector addition of electric fields, which we shall use to determine the null point location. So qualitatively, we have found out that at point C, that is to the left hand side of 4 into 10 power minus 6 Coulomb, a null point can never exist. So null point does not exist to the left hand side. What about right hand side? What about to the right hand side? Let me just write it down. Just a moment. Let's take this point C. Okay, let me make a change here. Let me redraw the diagram. This is 4 into 10 power minus 6 Coulomb. And this is going to be 16 into 10 power minus 6 Coulomb. Now A and B, I will call this as null point at C. Let's say the distance from A to C is x. In this case, the distance is going to be 6 minus x in this case, because the distance from A to B is already known to us as 6. Now at C, take a look at the positions of electric field. Electric field due to A is going to be pointing away from A because it's a positive charge. Therefore, this is the direction of electric field due to A onto the right hand side. Similarly, electric field due to B is going to be pointing to the left hand side this time. Why is this left hand side? Because it is a positive charge. Therefore, it is directed away from the charge. This is away from the charge and that's also away from the charge. Therefore, at C, this can be a null point. So whenever we have two positive charges, null point always exists between two charges. It exists between 2 point charges and it is always closer to the smaller charge. Now let us quantitatively find the value of x. To find the distance x, we are going to use superposition principle. Because electric field at C is equal to 0, which is basically the null point, this implies that electric field of EA plus electric field due to B, EA plus EB should be equal to 0. So this will happen if the magnitude of electric field at A, it is equal to magnitude of electric field due to B. Now we know that electric field due to a point charge is given by Q by 4 pi epsilon naught R square. So therefore, charge at A, what is charge at A? It is 4 into 10 power minus 6 divided by 4 pi epsilon naught. The distance in this case is x. So therefore, this is going to be x square. This is going to be x square. So electric field will be equal to, charge at B is going to be 16 into 10 power minus 6 Coulomb divided by 4 pi epsilon naught. The distance between them is 6 minus 6 the whole square. So 10 power minus 6 and 10 power minus 6 cancel, 4 pi epsilon naught and 4 pi epsilon naught cancels. To solve this equation, I'm going to take square root on both sides. What happens here? Once you take square root on both sides, square root of 4 is 2. Root x square is going to be 2 by x. Therefore, this is going to be root 16 is 4. And 6 minus x the whole square under root is just going to be 6 minus x. Now we can solve for x. Solving for x, we have 2 into 6 is 12. 12 minus 2x will be equal to 4x. 12 will be equal to 4x plus 2x, which is 6x. So therefore, x will be equal to 2 meter. So the null point exists. Null point exists. So if this was the distance, this was the figure that was given to us. This was 4 into 10 power minus 6 Coulomb. And this is at a distance of 6. The charge is 16 into 10 power minus 6 Coulomb. So null point exists at a point of 2 meter from the smaller charge. And from larger charge, it is about 4 meters. So one could take different values of charges and then find the position of null point. See, in this case, I have taken one positive charge and one negative charge. Let us apply the same principle that we have learned in the previous problem. So we have 2 into 10 power minus 6 and minus 4 into 10 power minus 6 Coulomb. And let's keep the distance to be 6 meter itself. Now tell me from the question, which is the smaller charge? If you tell me the smaller charge is minus 4 into 10 power minus 6 Coulomb, the answer is wrong, because the smaller charge here is 2 into 10 power minus 6 Coulomb. Don't think about the sign next to the charge. Look at the magnitude of the charge. So magnitude wise, the smaller charge is 2 into 10 power minus 6 Coulomb, and minus 4 into 10 power minus 6 Coulomb is still the larger charge, right? So therefore, from the principle that we've already learned, null point is always found closer to the smaller charge. So which in this case is 2 into 10 power minus 6 Coulomb. So it could be to the left hand side or to the right hand side. If it were to be at the right hand side, the direction of electric field due to 2 into 10 power minus 6 Coulomb, because this is a positive charge, it's going to be along which direction? It is going to be away from the charge, to the right hand side. Now because at B we have a negative charge, let's call this as EA. Because B is a negative charge, the electric field at point B will be directed towards the charge, because B is a negative charge. Therefore, this is the direction of EB. So because the electric fields are in same direction and they add up, and the net result is never equal to 0. So therefore, whenever you have two positive charges, or rather two like charges, the electric field always falls in between the charges. Whenever you have two unlike charges, the null point always falls outside the line joining of two charges. Take a look at this point. If I call this point as, if I take directions of electric field at this point to the left hand side of 2 into 10 power minus 6 Coulomb, electric field due to A will again be pointing away from the charge, which is to the left hand side, EA, while this time the electric field due to B will be pointing to the right hand side. Why is this to the right hand side? Because it's a negative charge, and electric field due to a negative charge is always pointing radially inwards. So therefore, it falls outside the line joining of two charges. So I will leave this as an exercise for you to find the exact null point where you will have to calculate quantitatively and find the distance. I will also give you an assignment problem so that you can solve it for yourself. The problem that I want you to solve is 1.8. Problem number 1.8 from your NCERT textbook. This has been asked in board exam perhaps in 2017, March 2017. Kindly go through. Right. The next type of problem that I want to talk to you about is the net force and net electric field problems in case of regular geometric shapes such as triangles, rectangles, and squares.